is the static test stand. Let me point out a couple things before we go through the parts that are kind of more important for your checklist. The first thing is how we get the data. So Trudy mentioned we have 2 dynamic load cells. So those are screwed in right here, and then their cords go up into the data acquisition system. So it's important to be aware of where the cords are when you're moving back and forth back here, as well as when you're putting stuff onto the static test stand. These cords are very fragile, and they're very expensive and very problematic and difficult to repair and replace. So be aware of where they are and don't cut them, please. The other thing, these load cells, we see this all the time in senior projects. You put a load cell to measure something, and then you think that it provides enough support for whatever article is under test. These load cells are pretty small, and they don't support any loads off axis. So they only measure in one direction, and they don't really do a good job supporting anything. So what we've done is we've added 4 bearings, 4 linear bearings, so 1, 2, 3, 4, that support or that allow this top plate to only move in the vertical direction. So any kind of side forces like this or any kind of torques are taken up by these bearings to protect the load cells down there. So that's really important, just for your future designs. Now this plate up here is the bottle mounting plate, or whatever you want to call it. You can see inside here there are some female threads that correspond to the Coke bottle threads. So you might not notice, or might not know this now, but Coke and Pepsi have slightly different threads, and they also have slightly different lengths of the throat of the bottle. Okay, so that's important. That's why we restrict all of our stuff to Coke bottle. Everything we've done is Coke. We don't necessarily have a preference. We're not sponsored. It's just that's what we started with, and that's what we've gone with. All right. The other thing is this red dot up in the corner. So this is really critical as well. There's a red dot in this corner and a red dot on the load cell plate in the corresponding corner. When I set this in place, you can see how that plate matches very nicely with the corresponding hole, the pocket that's been drilled in the other plate. If I were to flip it around, obviously this isn't going to work, but if I were to flip it 180 degrees, you'd think that it would work, and it was designed that it would work that way, but it was machined incorrectly. So the student that made this plate here machined too wide of a gap on one side than the other side. So if you notice, if I try to clamp this down, it will clamp down on this side, not so much on that side, but more importantly for your data is look at what you see on this side. It's sticking up, right? So this means that the bottle, instead of being pointed completely vertical, perpendicular to this bottom plate, it's now off at an axis. Now, we've done a good job adding in these bearings to protect our sensor, but if your thrust is off like this and you're expecting it to be like this, what's the net result? It's going to be lower, right? It's going to be incorrect from what you would really observe out on the field. So it's very important that you line up those red dots. Okay? Let's see, a couple other important parts. This is how we keep the water and the pressurized air in the bottle. So we'll screw the bottle in here, and then we add this rubber stopper up through it, and this rubber stopper goes into the throat of the bottle, and it keeps all the water and pressurized air up in the spot. Now we need to put something on the underside of this apparatus so that it doesn't just fall out from gravity or the pressurized air. That's where this block comes in. So this little sliding block will come through here, and then we'll pull it horizontally out, and that will release this force holding the whole apparatus up into the throat of the bottle. Okay? So one piece of mechanical engineering that I want to show you, which is pretty nifty, is this little red system down here. This is called a thrust bearing. So it's a piece of plastic with some little bearing balls. It might not seem that impressive, but its purpose is to dramatically reduce the friction between this pull plate and the washers that are holding the rubber stopper up into the bottle. So I can pull this out really smoothly, really easily, even when there's pressure applied to the top of it. If you were not to have a thrust bearing and just had a flat washer against this flat plate, that friction coefficient is much larger. And then you start adding a lot more force, it becomes much more difficult to pull out. So again, not important for your checklist, but for future designs, if you're doing something like this, you should consider a thrust bearing. Okay. The other piece of the puzzle here is this air tank. So we'll cover the air tank a little bit more in depth when we pressurize everything, but realize there are two different gauges and we have a pressure regulator. So this top gauge shows us the pressure inside of the tank. So right now we're hovering around 85, 90 psi in the tank. For your checklist, it's very important that you confirm that the pressure in the tank is greater than the desired pressure for your bottle, which is 40 psi. Right, that makes sense. If this is only at 35 psi, you're not just going to somehow magically get 40 psi inside of your bottle. So we like to say if this is below 60 psi, let one of the lab assistants know and we'll fill it back up. Okay? I'll talk about the regulator here in a second. So everything I've talked about so far just takes one person, but when you're operating the static test stand, two people really help tremendously. So this is where my assistant's going to come in, my lab partner, if you will. Your lab partner, Dylan, his name is really Devin, but you can call him Dylan if you want to. We'll screw the top plate onto the bottle. Now you want it to be snug, but don't crank it down too much because then it's going to be too difficult to keep it, to get it off. Recall that this rubber stopper is what keeps the water inside, not this thread engagement. Okay. Now I'm going to soap up this rubber stopper. We're going to use a lot of
feed it through.
Yep. So I'm going to soap it up, and then what these guys are saying is we want to thread it through the bottom of the hole. If we just started like this and assembled everything, then we'd have to thread that back end through this hole down here and out, which is fine. You can do that if you want to, but we've found that it's a little bit easier to just thread that part like this. And then I'll put the rubber stopper in the hole, kind of make sure everything's lined up, and then shove it down there. It needs to be far enough in the bottle that we can get this pull plate installed correctly. Now before I install the pull plate, I want to orient my rocket plate such that it's easy for me to install it after the plate's installed. So right now I have the red dot over here corresponding to this red dot, which means I'll just have to flip it over and drop it in place. If this red dot were over here, then you'd have to flip and twist, and that's just not as easy. So it's completely up to you, but we found in the past that it works better if the red dot's located here and just do a roll. Now we have to think about which way does this pull plate want to go. So I said before I want to pull through this gap here out back. So we can just thread it like this. And then do I want to put it on this side or do I want to put it on this side? Any ideas? Yep, exactly. Now this should slide in pretty nicely. You might have to shove that thrust washer down a little bit more.
Usually you'd want to maybe soap up the rails too, just a little bit. But when you do that on the actual stand, you'll want to probably do that too.
So we're going to drop a little bit of soap here and a little soap here. So the soap helps clean everything, but it's more of a lubricant than anything else. Now, this is where the extra set of hands really helps. So one person's going to be focused on lining the aluminum plate up and installing it, and the other person is in charge of getting the ripcord correctly located and the hose correctly located. And then I'm just going to double check that my pull plate is installed. Okay? So now the rocket's on the thrust stand. But there's one really important piece that I haven't done yet. Any ideas? Exactly. You guys did a good job listening to the truth. So I want to clamp all four of them down, and you can hear this little click. That means it's engaged. Okay. If you just install like this, it's not engaged. push it all the way until it clicks. 4 times. Okay? So now what we'll do is we'll talk about the pressure tank. The bottle's set up with the stopper in there, and we can leave it set up forever. I mean, we're not losing any water, we're not losing anything right now. So before I pressurize the system, I want to double check with my team member on the inside that the VI is running. And then once they've confirmed that it's running, I'll come over to the static test stand and just push a little bit lightly around those load cells to make sure that it's being read correctly on the DAC and on the computer. That's a very important part to double check that everything is working correctly. Trudy, are you almost ready? Yep. Is the VI running? Okay. Okay. So Trudy said it will be running soon. In the meantime, we'll talk about what's going on here with this air tank. So I've already mentioned before, we have a main pressure gauge here, and then we have a valve. So this valve, when it's perpendicular to the line, is closed. When it's parallel to the line or in line with the line, that means it's open. The same thing with this valve up here, but we're not there yet. We follow the hose through and we get to this big black thing. Anybody have any idea what this is? This is called a pressure regulator. So this will regulate whatever pressure is upstream to the desired pressure as read by this gauge downstream. When we connect this like that, then whatever pressure is read by this gauge after I open this valve, of course, will be the pressure that's applied to the bottle. So it's important that we check this pressure on this gauge before we connect to the bottle, right? Because we have a system with a significantly higher pressure. If this regulator is not set correctly, then you would add too much pressure to the bottle, and then if you have too much pressure, you can't relieve it. So the way we do that is open up the tank. Now notice what the gauge picked up right away. It's like 45-50. So that would have been bad if we would have connected that right to the bottle. So let me set this incorrectly for now, just so you can see it. So let's say I come out here and my gauge is at 50. I need to adjust the regulator, and the way we adjust the regulator, it's written on here so you can see there's a plus with an arrow that points in this direction and a minus with an arrow that points in this direction. So I'm too high, so I want to decrease the pressure. So watch what happens when I decrease the pressure. My gauge should go down. I'm going to set it right at 40. Now this isn't the end of the story here, and I'm going to show you why. If I just open this a little bit and let some flow go through, my gauge now reads different. It now reads 35. So this is just a consequence of this type of pressure regulator. So it's good to keep this in mind if you ever work with pressure regulators. You need to let a little bit of air flow through them before the pressure that you get on the outside is correct. So because it's lower, then I could just add a little bit more pressure until it gets to 40, and then I'll just bleed the line a little bit and make sure that every time and time again it reads 40 psi. And then I'll push this little cap in, and that locks it. So now I'm not able to turn the knob. Double check one more time, and we're set. Then I'll connect my bottle hose to here. All right, Trudy, are you ready?
Yeah, will you press on it and give me a verification real quick? Thank you.
So Devin presses on a little bit. You'll be able to see when you do the demo inside, but you get little spikes on the
Okay,
So now that we're ready here, okay, we're going to pressurize. Now when I pressurize, it'll take a little while, and then notice what happens with the bubbles. They slow down, and they continue to slow down, and we've done some tests, and it takes about 10 or 15 minutes for those bubbles to stop entirely. But that's too much time, right? We don't need to wait 10 or 15 minutes between tests. So what I've been telling people is once you can start counting the bubbles, then you can stop the pressure, and then we're assuming that the pressure inside of the bottle is equivalent to the pressure as read by the gauge. So it's getting closer, closer, closer. So I feel like right now I could start counting those bubbles if I wanted to. Some of you are faster counters than others, but if you can count, then generally we'll be around this little spot. So now it's important that I shut off this valve, and then I'm also going to shut off the tank valve for safety. Now there's been some debate in the last couple years whether or not we should leave this air hose connected, but what we do when we actually fly is we have you remove the tank and get it far away from the stand. So we want to test the same way that we fly. So I'll disconnect this, and then I'll move the tank over, and now I have a bottle with air pressure in it. All right, so I can leave this set. I'm not getting any leaks, I'm not losing any pressure, but I don't want to leave it on the test stand for too long, right? It's basically a live rocket at this point. So we'll confirm with Trudy that we're ready to go, and then you want to give the rip?
It's stressful, but I'll do it.
One safety thing. When this rocket loses its fuel, basically, it's going to go down into this gulch here, and there's a bunch of rocks and nasty dirt and whatnot. That's going to get sprayed out in this line, as well as perpendicular in this line. So if you guys want to get wet, you can stay there. If you don't want to get wet, you can move. Yes.
Yeah, we're ready.
So, Trudy, we're ready when you are.
We're at 2?
No. Devin's going to start the countdown at 5.
All right, so 5, 4, 3, 2, 1.
There we go. So you can kind of see the splash zone here. A couple things to take note from your memory. When Devin pulled it here, he used 2 hands and pulled that ripcord horizontal. So to get that plate moving in the correct plane. If you pull up too high, then that plate has a tendency to get jammed and you can't really pull too low. Also, if you pull it up too high, then the natural tendency of that aluminum mass is to go right into the window. We want to avoid that, so keep everything pulled nice and low. Anything else?
I think that's about it.
So another thing that I want to point out, because it might be a little different depending on the data you test, these aluminum I-beams. So we've added those to kind of help you see what's going on underneath it for the purpose of the demo. We may or may not install those for the actual test, kind of depending on how we feel like it. But the results are exactly the same. So the way this works is there's a piece of all thread that goes all the way through this plate and attaches to a stainless steel welded bracket that's rigidly attached to the channel, and that's what secures the bottom plate to the hood. So it doesn't.
Also, Bobby mentioned earlier, but these cables are very expensive and hard to repair, so make sure that you're just not stepping on them at all. Just be very conscious about walking over them and not tugging on them or anything like that.
Anybody have any questions? All right, so then